Welcome to Sundar's lecture. This is lecture number 63, and in this lecture we are going to see discharging energy from inductor in RL circuit. Just we are going to take the same RL circuit and we are going to see how the energy stored in inductor can be discharged in the load resistor. Before that, we will complete one topic. In the previous class we have seen this, right? What is this? What is the circuit diagram we have seen in the previous class? We have taken this circuit and then we have stored energy in the inductor. Yes, that energy, which is nothing but it is E by R, right? So this is the current in the inductor that will flow forever inside the inductor, right? Now, what will be the voltage? What will be the voltage in the inductor? This is the current curve, and we know that it will start from 0. At t is equal to 0, it will be 0. At t is equal to infinity, we will get E by R value, right? And I have already told you, it will not get to infinity time for E by R current, right? I have told you, it may take 1 or 2 tau to get the value of E by R, right? Now we try to find what is the voltage across the inductor. Now we know this is the current expression, so I will write it down. So we know that I of t, which is equal to E by R into 1 minus e power minus R by L into t. This we know. And what is the voltage across the inductor? We know that VL, which is equal to L into d by dt of I of t. So we can substitute in this expression, right? So L into d by dt of 1 e by r into 1 minus e power minus r divided by L into t, right? This value, and in this E by R is a constant value, so you take it outside, so you will get EL by R, and if you differentiate 1, it becomes 0, so it will not come. So next one, if you differentiate this one, see d by dt of minus is already there, this is 0, and if you differentiate this one, you will get the whole term will become in before that, so it becomes plus r by L, and then it will be e power minus r by L into t, right? So this is the differentiation of this term, and this L and this L, this R and this R will be cancelled out, right? Then what we will get finally? So finally VL should be is equal to E, this E, and then it will be maybe, right? So e power minus R by L into t. So this is the voltage in the inductor, voltage across the inductor may be. So if you draw the diagram, let me draw the graph for this. So same thing, just we will take the voltage VL in the y axis, this is VL, and maybe we will take this as the time axis, and if you put t is equal to 0, maybe you take it this expression number 3, t is equal to 0 in 3, what you will get? If you put 0, it becomes minus 0, and if it is minus 0, then the whole value will be 1, right? Whole value will be 1. So VL, which is equal to E into e power minus, if it is 0, so it will be 0. So it will be minus 1, totally 1. So VL will be what now? VL will be is equal to E at t is equal to 0. So at t is equal to 0, this is 0. At t is equal to 0, maybe if this is E, so t is equal to 0, my value will become E, and if you put t is equal to infinity, t is equal to infinity in expression number 3, what you will get? So VL will be is equal to e power minus infinity, right? E power minus infinity will be what? It will be 0. Minus infinity will be always what? It becomes 0, right? So VL at last, VL should be is equal to 0. See, this is the curve now. So I will just draw. So it will increase to E, and then at infinity time it will become 0. It will become 0. So I will write it down. It is t is equal to 0. It is t is equal to infinity. That's all. So now this is the voltage graph, and we know this is the current graph. See, it is just increasing, and at infinity time it becomes E by R, and it is just decreasing at infinity time. The VL become 0. Voltage across the inductor becomes 0. So this is the voltage graph for inductor. You can easily find two different things. See, in current there is no step jump. See, it is just increasing exponentially in this curve. There is no step jump. See, in inductor current cannot be like this. There will not be any spike. There will not be any spike or step jump in current. But you see, in inductor voltage can have a spike. Voltage will have a step jump. So I will just write it down. So see, I have just written inductor voltage can have a step jump or spike, but current cannot have a step jump or spike. It can increase exponentially or it can decrease exponentially. That while retrieving or discharging energy, it will decrease exponentially. See, but a voltage can have a spike. This one you have to very clearly understand, because this inductor will be used in the power electronics. And nowadays power electronics are pretty much used in all the applications. So inductor, knowing basics of inductor is very important. It cannot have a spike in a volt current. It have a spike in voltage. That point you have to clearly understand. Anyhow, we try to go to the next topic now. So this is the energy. Now we know what is the energy stored in the inductor, right? How an energy can be stored. We have seen with this example, maybe we have seen here, right? How we can store energy in the inductor. Now what is the thing? We need to find what is the discharging capability of the inductor. Now let me assume that first case number one, and we know these kind of things. I will just go through fastly for the case number one. So for case number one, it is switch is at position A, at position A. If switch is at position A, then what happens? Then this inductor will be connected across RL circuit, right? Then this inductor connected across RL circuit, right? What is the I of t formula? What is the I of t formula? I of t formula will be E by R into 1 minus e power minus R by L into t, right? And what is the voltage across the inductor? Voltage across the inductor will be E into e power minus R by L into t. That is what we have seen. That is what we have seen, right? Even though if it is not even connected to the short circuited, or it not, maybe it cannot be a short circuited one, but I of t and V of t will be this one. And you see, I have just drawn the graph for the I of t. Let we assume that this is the point. You carefully listen me, because this point you should understand. You carefully listen me. So maybe you take this as the t1 time. T1 time. And what is the current here? What is the current here? I am just assuming it to be I of T1, right? I of T1. Let it be any value. Let it be any value upon this. Maybe maybe you know that this point, maybe the final current value will be what? E by R. E by R. That we know that. But I will take some current, that T1, and then I am just saying that it is I of t1, right? Now you see we are going to take case number 2, and what is that? And we are going to switch can be now connected to, so switch is at position B. Now what we are doing, we are just closing this switch to B at no time, right? So now what will happen? So now this inductor will be, now connected with the resistor, right? So I will draw the diagram here. Now you see I have just drawn the diagram. This is the connection after switch is connected to point B. Now you see I am just taking this current, this current is already flowing in this direction. Now I am just taking this current as I of t dash to differentiate, because this is now connected. When switch is connected to A, this is the current is I of t, we have taken that, it as I of t. But now what I am going to do, I am just going to take it as I of t dash. See, when we have closed this switch at t is equal to t1, at this instant, at this particular instant, what I have done, I have just connected this switch to P. Try to understand, at this position, at this time, I am just closing switch is at position B. I have just connected, right? Just I am taking it as I of t dash now. So how this current will flow now? This is plus and this will be minus, and it will flow like this, right? If I write a KVL expression for this one, the current is flowing in this direction, so what I will get, it will be minus I of t dash into RL, and then it will be flowing from plus to minus, so it will be minus L into di by dt. That should be is equal to 0, right? This is the expression now. So now what we can do, we can write this expression as I of t dash into RL minus di of t dash. This is also t dash, right? You just write it down. It has I of t dash divided by dt. This is plus, that should be is equal to 0. So I am just changing, signs has been changing, right? So now what we can do it here, we can just integrate on both sides. What we will get, so before that we try to divide by L on both sides. This is we have done before. On both sides, what you will get, you will get it as R by L into I of t dash, and then plus, oh sorry, I have missed L here, so if you divide L with this one, so you will get di of t dash divided by dt, and that should be is equal to 0. And what we are going to do now, very simple, right? Because if this is the first order differential equation and you just multiply with the integrating factor. What is integrating factor? Integrating factor, we have seen these kind of things, integrating factor, and I have told you I am just going to take it in the next class. I am going to take how to solve differential equation with the classical techniques, right? That we will see in the next class. This will be e power R by L into t, right? That is the integrating factor. I am just multiplying integrating factor on both sides. So it will be e power R by L into R by L I of t, plus here I will get e power R by L into t, and this will be d of t dash divided by dt, right? So this should be is equal to 0. Oh, here also you put dash because integrating factor, we are considering it to be I dash, right? So it will be like this. Now you see, compare these two expressions. It is nothing but it is UV, right? It is UV, right? So what we can do here, this can be written as d by dt of e power R by L into t dash, and then it can be written as I of t dash, right? That should be is equal to 0. It is simple, right? Because you see, we have to integrate this one with keeping this one as it is. That is what here we have done. We have just integrated, right? Everything you know. Before that, we have seen an expression like this in the previous class, right? So now what we can do, we can just integrate on the both sides. Integrate on both sides, what you will get, so you will get, if you this will be cancelled out, and finally I will get e power r by l t dash into I of t dash will be is equal to integrating constant. What you will get? You will get a, right? So this is the expression. So this one I can bring it to the other side. So I will write it in the next page. See one thing we have missed from the beginning. See, this is RL, right? So wherever you see, you put it as RL, right? Everything, it has to be RL, 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 RL. I have just missed it down. I have just used it as R. So everything it will be RL. Now what I can do, I can write the expression as I of t, this is t dash. So I of t dash will be is equal to a divided by this term, and if I bring to the numerator, it will be e power minus r by l into t dash. Now let me take this expression as number 1. So now we have found what is the I of t expression, right? Then if I want to find what is the value of a, then what I need to do, I need to substitute the initial condition, right? What is the initial condition here? What is the initial condition? I of 0 will be is equal to what? I of t1. That is what we have taken here. At this instant, what is the current here? What is the current here? It will be I of t1. At that instant only, we have just, what we have done? We have just switched this switch is connected to point B, right? So now this will be I of t. So if I just substitute this in expression number 1, this is initial condition, right? That we need to take it as initial, because we have switched this, with, sorry, we have just connected the switch to point B at t, I of t is equal to I of t1, right? So if you substitute this in this expression, instead of t, we need to put I of t1. So it will be a, it will be e power minus r by l. Instead of this t dash, you need to put t1, this one. So if you find what is a here, so I will write it in a different color. So a can be written as I of t1 into e power. This will be brought to the denominator, and if I bring that denominator to the numerator, I will get r by l into t1. Right, this is the value of a now. This is the value of a now. Right. So now I can substitute this a in expression number 1. So substitute expression 2 in 1, what you will get? So I of t dash will be is equal to a, which is nothing but it is I of t1 into e power r by l into what, t1 multiplication of e power minus r by l into t dash. Now, if you take minus r by l outside, this is the final expression. This is the final expression. Take minus r by l outside commonly. So it will be minus r by l. You take commonly outside. This will be now t dash minus t1. This is the final expression for what? For the switch connected to point B. That is the current now flow. This current will flow after switch is connected to point B. Anyhow, I'm just going to draw the diagram. Oh, sorry. This one I have just made it. Right. Now I'm going to draw the graphs. Clearly understand this graph. You just come with me. I will explain you. This is now I of t and this is now t. See what we have done. We have just connected the switch at point A, so that current will grow like this. Current will grow like this. And what we have done, at t is equal to t1, and the current at that position is nothing but it is I of t1. This is up to switch connected to point A, right? Switch is at point A. Switch is connected to point A, and this point we know now. So after this, what we have done, we have just connected the switch to point B. Now what we can do, you just substitute the values now. Now what we will do, we just substitute, make it as expression number 3. We just try to substitute t dash is equal to t1 now. What happens if t dash is equal to t1 in expression number 3? So it will be now I of t dash, instead of t dash I need to put t1, right? So I of t1 will be is equal to I of t1, which is e power minus r by l into, what is this value? What is this value? We have taken it as t1. So t1 minus t1, this will be 0 and e power 0 will be what? 1. And what happens to this expression now? So I of, maybe you just keep it as t dash. I of t dash will be what now? t1. I of t dash, if it is the initial condition, it will start from this point. And what we are going to do now, you substitute t dash is equal to infinity now. What happens to in this expression in number 3? What will happen now? I of infinity, I of infinity will be is equal to, see, if I substitute infinity, whole expression become infinity. E power infinity is what? E power minus infinity, sorry, e power minus infinity is what? 0. So it becomes 0. It becomes 0, right? This value, it is t1 and it becomes 0. What happens now? See, maybe different one. See, this will start from this point and it will be die down to 0. And it will be die down to 0. So see, this part, this part, this part is energy stored part. What we have done? See, when it is connected to point A, inductor will get E supply and it try to store energy. And what is the next? That is what we have seen in this graph up to this one. And what is this part? What is this part? This part is S is at point B now. So what we have done? We have just connected this inductor instantly to point B, sorry, this switch to point B, and now this inductor is connected to a resistor. And whatever the energy this inductor possesses will now discharge through the inductor. And that is what happening here. That is what happening here, right? So what is this one now? This is discharging, discharging energy from inductor. Try to understand one thing. So this is how you are just pumping energy into inductor and just retrieving or discharging energy from the inductor. If you connect any resistor across the inductor, then obviously it will transfer the energy to the inductor, right? So try to understand these kind of basics very well, right? Right, one thing I just want to tell you before the next class, because in the next class we are going to take the classical way of solving differential equation. Right, I will just write down the expressions for energy stored in inductor and what is the current expression for RL circuit. See, this is the expression for RL circuit, right? This is I of t. Try to understand this one, which is nothing but it is solution due to forcing function. Try to understand what is forcing function in our circuit. What is the forcing function? E is the forcing function. This gives because of this voltage we are pumping energy into inductor, right? So this is the forcing function, and that is what we have written it as solution due to forcing function. And what is this part? This part which is nothing but solution due to natural function. And why I am writing this one? See, solution, I'm just explaining things in a way of solving differential equation. After solving the differential equation, we have got this expression, right? That is what we have done, right? So see, in the previous classes, so many expressions. See this expression, which is nothing but this is the first order differential equation, and after solving the first order differential equation we got this expression, right? So in final expression, this part is solution due to forcing function, this part is solution due to natural function. See why I am saying this, because of natural function, because of R and L this function is existing, right? How much this solution due to natural function will be always zero, will be always zero. At some instant, at some time, this is going to become zero. Why? You can see that. What is the final I of t we have seen? See here. What is the final I of t we seen? We have seen it is E by R. And what happens to this expression? What happens to this one? This whole term? It becomes zero. It becomes zero at some time, a stipulated time. So solution due to forcing function alone can satisfy this I of t. See, right, to understand. This always becomes zero. And even you take this one, this is wholly solution due to forcing function, sorry, natural function. Why? Why? Because you see, you don't say that, sir, here it is E by R, here it is E. Why you are not considering it to be a forcing function? See, forcing function should be alone. It should not it should not contain E. Epsilon values will not be, exponential values will not be available in expression which we are saying it as the forcing function. See this one, actually it is natural function. Obviously this V of t will be 0. That is what we have seen. See what happens to VL, inductor. Inductor current will become 0. Right? So you try to understand this one very clearly, and we will continue in the next class. I am very happy to say that I am going to teach mathematics. See, as an electrical engineer or an electrical faculty, I really want to teach mathematics related to electrical engineering so that my students can understand mathematics and they can also relate that with the electrical engineering. See, I am going to solve a classical way of solving differential equation in the next class. Please be careful to listen my next class, because that class is going to give you many more insight towards solving differential equations. Thank you. We will see in the next class.